In this video I'm going to be looking at how we can find the pH of a weak acid from some data we're given rather than doing it just by using an indicator or a pH meter. So what I'm going to use is this comparison here, 0.150 moles per litre hydrochloric acid versus the same concentration of ethanoic acid. You'll see there's a thing up there called pKa for the ethanoic acid of 4.76. That's going to be very important for this as we move on. So the first thing I'm going to do is just quickly classify these two acids. The hydrochloric acid is a strong acid, which means it fully dissociates. That means when we put HCl into water, all of the HCl turns into hydronium ions and chloride ions. So therefore the concentration of hydronium in this is going to be 0.150 moles per litre. And same for the chlorides, but they don't have any effect on the pH. So to calculate this, all I'm going to do is use my pH equation. pH is equal to the negative log base 10 of the hydronium ion concentration. And so that is going to be negative log of 0.150. And so I'll quickly do that now. And we get 0.824. So that's our pH there. Unfortunately, or more interestingly I suppose you could say, the ethanoic acid is a weak acid. So that means it's going to only partially dissociate. Which means when we do it, we actually write it as an equilibrium. So I'm going to get rid of this one and show you how we do it for a weak acid. So ethanoic acid, CH3COOH, when it's put into water, actually quite a lot of the ethanoic acid molecules stay together. Only some of them dissociate, which means it's an equilibrium, becoming hydronium ions, just like in our strong acid example, and the ethanoate ion. Now, because it's an equilibrium, I can write an equilibrium expression for this. In this case, because it's an acid making hydroniums, it's called Ka. So Ka is equal to this. So if we can't remember how to do a K expression, maybe see another video or check some notes on writing equilibrium constants. But you'll see that I am not including water. That's because its concentration is constant on both sides of the equation anyway, to the number of significant figures we're looking at. So it can be excluded from this. Now, we actually already know some of these values. We actually know, looking at the equation, that these two values are pretty much the same in concentration. So let's, for argument's sake, call that X. We also know that because it's a weak acid, the concentration of the actual ethanoic acid molecules has hardly changed. So we're going to assume that that stays at 0.150 moles per litre. Now it may only be correct to two significant figures now, but we can still use that same number. We actually can find Ka. The way we can find it is that we have the pH. So to find the pKa, we can turn pKa into Ka the same way as we turn pH into hydronium ion concentration. That is, that the Ka is now going to be 10 to the power of negative 4.76. Now that's not a real number, as it were, but it can be put into our calculator that way, so we can actually leave it as this incorrect, mathematically incorrect statement. So to rearrange it, we actually are going to be able to find something. To find the pH, we want to know the hydronium ion concentration. We've made an assumption that the hydronium ion concentration is the same as the ethanoate ion. And we've called it X for simplicity. So if I was to rewrite this equation, it becomes 10 to the power of negative 4.76 equals X squared, because this is X and this is X, over 0.15. I'm taking 0 off, it's not important at the moment. So I can rearrange that to be x equals the square root of 10 to the negative 4.76 over 0. Sorry, I've made a mistake there. Apologies, not divided by its times. Over the square root of 10 to the negative 4.76 times 0.15. Okay? Now the other way that I could write that, so that I can remember something in the future, is like this. Hydronium ion concentration for a weak acid, okay, this is only for a weak acid, equals the square root of the Ka times the acid concentration. So that's something I could remember. It's also just as easy to rearrange it, but if you want something to remember for your exams, then there's a little equation you can use. So when I solve this, I do that now. I get the x squared is 2.61 times 10 to the negative 6, so therefore x is 1.61 times 10 to the negative 3. Now this is a concentration, so I have to remember my unit is moles per litre. And now I'm actually going to cross out my x and make it say what I want it to. Hydronium ion concentration. Now I know how much of this is made, I can work out pH. pH equals the negative log base 10 of this. Which is 2.79. Okay? Relatively low pH for a weak acid, but that's because its pKa is relatively high. So just to summarise the key steps for a weak acid, this one here, which is going to have a much higher pH, you'll notice, than 0.8 that it was for the strong acid. Just to summarise the steps, first of all I write a Ka expression from the equation. I substitute in x here. I assume that the concentration of the acid has hardly changed from the original question, and then I solve, knowing that x is also the hydronium ion concentration. After I've got the hydronium ion concentration, I can calculate the pH using negative log base 10 of that hydronium ion concentration.